Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog. Good evening. Tonight we welcome Dr. Colleen Dalton. Dr. Dalton is a Massachusetts native after receiving her BS degree in geophysics at Brown University. She worked for an environmental consulting company and then obtained her PhD in geophysics from Harvard in 2007. She followed that with a postdoc position at Columbia University and then joined the Earth Sciences faculty at BU in 2008. Dr. Dalton's research focus is earthquakes, and specifically how the seismic waves generated by earthquakes reveal the structure of the Earth's interior. Her work is crucial to the understanding of deadly forces such as we've witnessed in the last several months, particularly in Haiti and Chile. She'll tell us how she develops and models information about the forces that cause earthquakes and why the level and types of seismicity vary from place to place. Please welcome Dr. Dalton.
Good evening. When Yvonne and I set up this date for this lecture, it was back in the fall many months ago, and we had no idea at that time the extent to which earthquakes would dominate the news headlines in the winter of 2010. And it's almost always a bad thing when earthquakes dominate news headlines, as they have in January and February of 2010. So today I'll talk a bit about what causes earthquakes, especially the types of earthquakes that we've seen in Haiti and Chile this winter. I'll talk about where we find earthquakes and those processes. And then if I have time at the end, I'll talk a little bit about one possible example of the way in which earthquakes can actually be useful to us. The picture here on this first slide is an image from a wood cutting. And this image illustrates damage that was done to Boston due to an earthquake that occurred in Cape Ann, up north of here, in 1755. Even though this earthquake was several tens of miles from here, it caused considerable damage in Boston. Records show that perhaps as many as 2,000 chimneys were toppled during this earthquake, and several brick walls of buildings crumbled. And I show this image to illustrate that even though we don't often think of Boston as a place that has earthquakes, in fact, there is a history for seismicity in our own backyard. Most people probably are aware that a couple of weeks ago, in late February 2010, a very large earthquake occurred on the west coast of Chile. This was one of the largest earthquakes in the recorded record, and its location where it began is shown here at the red star towards the bottom of the coastline. Perhaps as many as 500 people or even more have been reported to have been killed as a result of this earthquake, with 500,000 homes damaged. This image here shows destruction caused by the collapse of a highway near Santiago, Chile as a result of the earthquake. And here we see collapse of an apartment building near Concepcion. Here, a bridge collapse a couple hundred miles from the epicenter. And of course, you may have also heard that the earthquake in Chile did generate a tsunami. And so this image here shows a fishing boat, which originally was located in the water, that was brought ashore by the massive waves caused by the tsunami offshore South America. And again, similarly here, these shipping containers were washed ashore as a result of the tsunami. And about 6 weeks prior to this earthquake in Chile, there was a separate and large earthquake that occurred in Haiti. These two images show maps of the general region where the Haiti earthquake occurred. In the top map here, we see a bit of a zoom out where we can see Central America and part of the Caribbean. and Haiti is on the island of Hispaniola. It takes up the western side of this island with the Dominican Republic on the right-hand side, and the epicenter of the Haiti earthquake is shown by this red dot right here in the bottom panel, and it occurred about 20 miles west of Port-au-Prince, which is the capital city of that country. Due to a number of factors that include the fact that it was a shallow earthquake, and the fact that it occurred in a very densely populated area, and the fact that the area has less than ideal building practices, this earthquake has been extremely damaging to the region, with perhaps as many as 200,000 fatalities and at least 1 million people left homeless. Even the presidential palace was not spared during this destruction, and its 3 stories have collapsed in on itself as a result of the strong ground shaking. And this image here shows the utter destruction of a hillside neighborhood in Port-au-Prince. So I think it's very clear that earthquakes have enormously damaging potential, and it's essential that we continue to try and understand these massive events so that we have some hope of being able to mitigate the disaster in the future. So to talk about earthquakes in a little bit more generally, I think we should step back for a second and let's think about what we actually know about earthquakes. And one thing that we know about earthquakes is where they occur. This image here is showing the earthquakes and their locations that have occurred in the past 365 days, so the past year. And the different colored symbols in the map correspond to the depths of the earthquakes. So the blue and purple are earthquakes that didn't occur very deeply in the crust, maybe 20 or 30 miles down into the crust. And then green, yellow, orange, and red here are earthquakes that occurred several hundred miles into the Earth's mantle. So what are a couple of things we notice about this map of earthquake locations? Well, I think the thing that really jumps out to most people is that earthquakes do not occur everywhere, and in fact, they seem to occur again and again in certain places. There are very well-defined belts of earthquakes around the Earth where we see these earthquakes happening. For example, in the middle of the Atlantic Ocean, here in between North America and Eurasia, we see a belt of earthquakes, all purple, so all occurring at shallow depths. And up through the Indian Ocean, we see these earthquakes, and into the Pacific, and of course, lining the western rim of the Pacific Ocean. And we also see earthquakes occurring along in continental areas. So a number of them occurring north of India here, where the Himalaya mountain range is. A number of them occurring along, for example, western North America and the western USA. You can also see that in some places we only see shallow earthquakes. Like, for example, I pointed to a number of places in the middle of oceans. And in some places we see shallow earthquakes and deep earthquakes. So we see deep earthquakes along, for example, western North America. We see deep earthquakes in the Aleutian Islands off of Alaska. We see deep earthquakes all along the western Pacific over here. So there's clearly some geographical stratification of where earthquakes of different depths occur. And of course, there is a reason for this, and we think that we understand it quite well, actually, and it's due to a phenomenon known as plate tectonics. And the theory of plate tectonics states that the Earth's outer layer, is rigid, and it's divided into a number of plates that move relative to one another. So this map here shows the entire globe. And first, let's talk about the colors that are plotted here. The colors here show topography of the continents and the depth of the seafloor. So the oranges and reds and yellows and greens, those are continental areas, and the redder the color, the higher the topography. So places where we know that there are mountains, like, for example, the Rocky Mountains in the western US and the Himalayas over here in Asia, are places with high topography. And in general, all of the continental areas have high topography. We sit above sea level conveniently. And the blue areas are, of course, the ocean floor. And so there's this distinction in the topography between the continents and the oceans that really jumps out at us initially. And then the white lines on here show the shapes of each of the individual plates. And a lot of them are given names that actually make a lot of sense. So for example, the Pacific plate is the largest of the tectonic plates, and it encompasses much of the Pacific Ocean. So this is this plate here, if you can follow the arrow that encircles a lot of the Pacific Ocean, but not all of it. A lot of the plates that have continents have names that are the same as the name of the continent that's on the plate. So for example, the North American plate, of course, has the continent of North America, and it also has a little bit of oceanic material as well. And the Eurasian plate has the continent of Eurasia, the African plate has the continent of Africa, South American plate has the continent of South America, and so on. And then there are also a few smaller plates. So for example, you can see this plate down here just west of Central America, that's the Cocos plate. This plate down here just west of South America, that's the Nazca plate. And there's a little tiny plate up here just west of North America, and that's the Juan de Fuca plate. So there's a diverse range of plate sizes and also whether or not they have continents or oceans. The Pacific plate mostly just has ocean on it. And these plates move relative to one another. And so if we go back then and look at the distribution of earthquakes over the past 1 year, now their locations, I suspect, make a lot of sense to you. Almost all of the earthquakes are occurring along these known plate boundaries. So for example, this belt of earthquakes that runs down the middle of the Atlantic Ocean corresponds to the plate boundary between, say, North America and Eurasia in the northern part of the Atlantic, and the plate boundary between South America and Africa in the lower part of the Atlantic Ocean. And same thing here, we can follow into the Indian Ocean. This belt of earthquakes represents the boundary between the African plate and the Antarctic plate. And then over here between the Antarctic plate and the Indian-Australian plate. And furthermore, these places where we saw deep earthquakes and shallow earthquakes, like along western South America and along a number of regions in the Western Pacific, are also, plate boundaries. For example, here, the plate boundary between the Pacific plate and the Eurasian plate, we have earthquakes there. And the plate boundary between the Pacific plate and the Indian-Australian plate down here, well, we also see earthquakes. So we have a pretty good understanding then of why we see earthquakes occurring again and again in these places. And interestingly, not all of the earthquakes occur along plate boundaries. So you can see in this map here that there are actually a handful of earthquakes that occur in eastern North America, and we are nowhere near a plate boundary. So these earthquakes clearly require some other explanation. And there's also a bunch of diffuse seismicity up here within Eurasia. But for the most part, it's safe to say that the majority of the earthquakes occur along plate boundaries. And it's not only earthquakes that occur along plate boundaries. In fact, we see similar things with the distribution of volcanoes. So this map here is showing the location of active volcanism, and it's mostly shown by these little red dots that are in some places hard to see. And so we see some familiar volcanoes. For example, up over here would be Mount St. Helens. And of course, we know that Hawaii has active volcanism, and Iceland has active volcanism, and a number of other places that I'm sure you've heard of. And so you can see that a lot of these volcanoes fall along known plate boundaries. So for example, down here, the boundary between the Nazca and the South American plate, just west of South America, a lot of volcanism down there. And up here in the Aleutians, the boundary between the Pacific plate and the North American plate, a lot of volcanism there. So plate tectonics is able to explain a lot of observations of earthquakes and volcanoes. However, I should note there are some volcanoes that aren't explained by plate tectonics. So for example, Hawaii actually is in the middle of the Pacific plate, not along a plate boundary. And we have explanations for those things as well, but I won't get into that today. So the plates move relative to one another, and you're probably asking yourself, well, in what sense do they move relative to one another? And you hopefully can see on this figure here that each plate boundary has a set of arrows. And in some cases, the arrows point away from each other, like here between the Nazca plate and the Pacific plate. The arrows point away from each other, suggesting that the Nazca plate and the Pacific plate are moving away from each other. And in some places, the arrows point towards each other, like over here, the Nazca and the South American plate, the arrows point towards each other, suggesting that the plates are moving towards each other. That's also true along much of the Western Pacific. We see the arrows pointing towards each other. And then in a couple of places, we see arrows that are not pointing away from each other and are not pointing towards each other, but are actually just pointing side by side. And the best example is up here in California, the San Andreas Fault. And so really there are then three types of plate boundaries, three types of ways the plates can move relative to one another. They can diverge or move away from each other. They can converge and move towards each other, or they can be a transform boundary, which means that they move side by side. Divergent plate boundaries are places where the two adjacent plates are being pulled apart. And this little image up here on the top left shows just a schematic of that, where you have one plate on the left and one plate on the right, and they're being pulled apart from one another. And as a result of the fact that you pull the plates apart, you create a space, and so magma upwells into that space to fill the gap, and we have volcanism there. And the best example of divergent plate boundaries are mid-ocean ridges. So these are ridges that run down the middle of the ocean floor. It's like a mountain range with some volcanism on the ocean floor, and the Mid-Atlantic Ridge, which runs down the center of the Atlantic, is really one of the best examples of a divergent plate boundary. At the same time, there are a few examples of divergent plate boundaries that actually occur on continents. And this is a case where, again, you have two pieces of continent being pulled apart from one another. That's what the schematic on the upper left shows here. And magma upwells to fill in that gap created by the fact that you're pulling two plates apart from one another. And a very good example of this active divergent plate boundary on a continent today is in the East African Rift. So the figure over here on the right is a zoom in on the eastern part of Africa, so Ethiopia and Tanzania, the Red Sea, the Gulf of Aden. And you can see here these arrows indicate the direction of motion. So this is a place where the continent of Africa is actually in the process of being split in two. So it's a process of going from being one coherent plate to two separate plates. And eventually, we suspect, this boundary here that goes in between the arrows will represent a plate boundary between new plates. So this is an incipient divergent plate boundary. And it explains why we have a lot of lakes in this area, because doing this creates depressions that allows water to infill. And it also explains why we have a fair amount of volcanism in this part of Eastern Africa. So that's one type of plate boundary, divergent plate boundaries. Convergent plate boundaries are variable as well, and we can put them into three main categories. Let's focus on the top left here first. I've called this an ocean-ocean convergent plate boundary. So this is a place where an oceanic plate meets up with another oceanic plate. And so one of the oceanic plates then has to descend or sink beneath the other one. Generally, whichever one is denser is the one that sinks back down into the earth. And so this is called a subduction zone. This is how we recycle crust and mantle material from the surface back down into the deep earth. And at an ocean-ocean zone, you have two oceanic parts of plates colliding and one descending into the mantle. So at these places, again, we see volcanism, and we often see arcs of islands. And I'll show you an example of that in a minute. On the upper right over here, we have a second type of convergent plate boundary. And this is an ocean-continent plate boundary. So this is a case where an ocean plate meets a continent plate, and always the ocean plate descends beneath the continent plate. The continental crust is more buoyant than the oceanic crust, and so it's less likely to want to sink back into the earth. It's too buoyant, whereas the oceanic crust and lithosphere are denser, and they do descend into the mantle and get recycled there. And then finally on the bottom here, we see an example of the third type of convergent plate boundary, a continent-continent plate boundary. And this is a place where two continental plates meet. And it's pretty tough because neither of them really wants to sink. They're both buoyant, neither of them is very dense. And so generally, instead of subduction and instead of recycling some crust and mantle back into the Earth's interior, we build up a high mountain range. And it makes sense that we would have to have convergent plate boundaries, because we talked about how at spreading center, we're pulling apart plates and creating gaps, creating new space and new material. And since the Earth isn't expanding, there needs to be a mechanism for which we also destroy some material. Since we created at divergent plate boundaries, we destroy material at convergent plate boundaries and maintain and keep constant the size of the Earth. And here we see examples of each of these three types of convergent plate boundaries. Up here on the upper left, The Aleutians, just off of Alaska, within the Bering Sea, are a very good example of an ocean-ocean convergent plate boundary. And this is a place where the Pacific plate is descending underneath the North American plate, and the Pacific plate is being recycled back into the mantle. And I said that we get volcanism occurring at these places, and indeed this Aleutian arc here is an arc of a string, a chain of islands, and all of them have been created by volcanism that's produced as a result of this collision. On the right over here is an example of the second type of plate boundary, a second type of convergent plate boundary, an ocean continent. And one of the best examples on Earth of an ocean continent plate boundary is the Peru-Chile Trench. So this is where the Nazca plate, an oceanic plate, is descending beneath the South American plate, a continental plate. And so we know, of course, that in this area we have the tall Andes Mountains, we have volcanism, and of course we have large earthquakes. And then finally, the third type of plate boundary, where a continent and a continent collide and neither really wants to descend into the Earth. The Himalayas are a very good example of that. So this is a place where the continent of India is colliding with the continent of Eurasia. Neither of them wants to sink, and so instead they have built up this massive mountain chain of the Himalayas that extends forever, really. It's huge. So those are two types of plate boundaries, divergent and convergent. And then the final type is this transform plate boundary, where the two plates just slide by each other. And the best example on Earth of this is the famous San Andreas Fault in California. In this map over here on the left, you can see the tectonic plates in the region. And what we have going on here is that the Pacific plate, where the Pacific Ocean is moving up to the northwest. And the North American plate, where we are sitting, is moving down here to the southeast. And so those two plates move by one another. There's obviously a lot of friction involved in that, and it generates earthquakes. And interestingly, Los Angeles is on the Pacific plate, and San Francisco and much of the Bay Area is on the North American plate. So if we wait 10 or 20 million years, which is a long time, then Los Angeles and San Francisco will actually be side by side instead of separated by several hundred miles. And on the right over here, I have a couple of pictures. Transform plate boundaries are neat because we are able to see them sometimes from airplanes. And on the top panel over here, you can see a picture of an orchard. And hopefully you can imagine that probably whoever planted this orchard planted the trees in straight lines. But now you can see that there's this region across which the lines of trees have been offset. And this is an example of a place where you have a transform plate boundary. You have one side of the plate moving relative to another. And similarly, in the map or the image down here in the bottom, this is a dried up stream bed or a creek bed, and you can probably picture that at one time the creek bed over here on the top part of the figure connected directly with its continuation down here in the bottom part of the figure, but a transform fault passes through this area and has offset the bottom side of the creek relative to the top. It's offset it to the left. All right, so now that we've covered plate boundaries, let's get back to talking about earthquakes. And almost all earthquakes occur on faults. You probably knew this. And there are some nice examples of faults in real life. Faults are places where we have a fracture in the rock, and so the two sides of the rock on either side of the fracture are able to move relative to one another. So here in this figure, this is a picture of a road cut in which we can see that the rock has obviously been fractured and then the two sides displaced relative to one another. In particular, the left side of the fault here has been displaced down, and the right side of the fault has been displaced up relative to the other side. And a more recent example, this is probably a fault that slipped quite some time ago. This is a more recent example from an earthquake that occurred in Taiwan in 1999. This is an athletic field, and you can see the remnants of the track of this athletic field here. And the left side of the figure I'm showing you moved upwards relative to the right side. So it really cracked and deformed and destroyed or distorted the track, and you can also see that it did that here for the grass. Presumably this was actually a flat playing field before the earthquake occurred and there was slippage on the fault. So the theory for how how faults slip and why faults slip and give us earthquakes can be explained pretty simply with something called elastic rebound theory. With elastic rebound theory, a lot of times we use an image of a fence on someone's farm to illustrate this. It's a very simple illustration. And shown here are the positions of this fence at 3 different time periods. So unfortunately, whoever built this fence didn't realize that he was building it across a transform plate boundary or across a fault. And so initially he builds the fault and it's flat and straight all the way across. But there are 2 plates. There are plates on either side of the fault, one moving upwards and one moving downwards. And so over time, the 2 sides of the fence start to move relative to one another. However, there's a lot of friction on the fault, and the friction holds the fault together. So while the areas away from the fault are moving in response to the tectonic forces, the area right around the fault is locked due to these frictional forces. And so this keeps happening until the friction on the fault is no longer strong enough to keep it locked, and the fence then straightens out and we get displacement. We get a little bit of slip on that fault, the fence straightens out, and we have now an offset fence. And this is not only a theory, there's evidence of this. This is an older figure from an area in Northern California where you can see a fence that was presumably at one time straight all the way along its length and now clearly has some very clean offset as a result of slippage along the fault. Here's a little movie that'll show you the effects of this elastic rebound theory. So it pretends that we have a farm full of apple trees, but that there's a transform fault that moves through the orchard and offsets the 2 sides. I'll play it once so you can get a sense. So you can see the left side of the image is moving up and the right side of the image is moving down. So you have relative motion of the fault, but the fault is locked. And so until there's an earthquake, which shakes the apples from the tree, the 2 sides of the fault remain stuck by this frictional force. But when the frictional force can no longer overcome the fact that the 2 plates really want to be moving relative to one another, then there's an earthquake. I'll play it for you one more time. So again, you can see up on the left, down on the right, but locked right at the fault zone, and then earthquake shakes the apples from the trees, and now we have the orchard being offset instead of straight lines of trees. So when there's an earthquake, it generates seismic waves, seismic energy. A lot of the seismic energy, if you're near the earthquake, creates a lot of ground shaking and a lot of the destruction and damage that I showed you in the beginning. But these earthquake waves, seismic waves, they radiate out in all directions from the epicenter or the focus of the earthquake. And there are 2 primary types of earthquake waves. One type is called body waves. Now body waves, they dive deep into the Earth's interior, then they travel back up to the surface. And we talk about both P waves and S waves when we talk about body waves. And then the second type of seismic waves are surface waves. Those travel more slowly and they travel along the Earth's surface. So those tend to be the waves that actually cause a lot of damage nearby. This is a cute little movie. It's a little cartoonish, but I think it illustrates the effects of both the P wave and the S waves. So those are the body waves and the surface waves. So there's going to be an earthquake over here, down in the lower part of the screen, and it's going to send out P waves and S waves, and then some surface waves, and you'll see the little houses and the cow on the surface be affected by these propagating waves. So give it a look. Okay, so there's the earthquake down there in the lower right. Now the P waves travel faster than the S waves. So the P waves are already heading up. They dive down into the center of the Earth, and then they head back up to the surface where they, in this cartoon at least, shake the surface a little bit. Now the surface waves are traveling along the surface, and they're just now getting to that cow, and they make it rattle a little bit, and then they rattle that house. But you can see that they're traveling rather slowly as compared to the body waves. The body waves have come and gone a long time ago. And then in this panel down here that's inset within the movie, what you're seeing is the ground motion as a function of time. So the red were the P waves. So at A, B, so A is very near the earthquake, it's a little house, and then B is a little bit farther away from the earthquake, C is even farther from that, and D the farthest of all of these 4 houses. So we're seeing the shaking occurring at each of these houses. And red is from the P waves, blue is from the S waves, and the orange is from these surface waves. So you can see that the farther the station is from the earthquake, the longer it takes those waves to get there. And let's give that movie one more look. Okay, so there's the earthquake, there goes the P waves, they're really taking off. They travel fast, they dive down into the earth, and then they come back up to the surface. And the S waves are trailing behind by just a little bit, and eventually they too get back up to the surface, and then those pokey surface waves are just taking their slow time, moving parallel to the surface of the earth at a much slower speed. So the surface waves are just now getting to house C. And this is, in a very simple way, how seismic waves do travel inside the Earth. And fortunately, we have a very nice network of sensitive seismometers that can record very, very small ground displacements. And these seismometers are distributed around the globe, and they're constantly recording ground motion. So anytime there's an earthquake that's large enough to be recorded, we do get a record of that ground displacement in nearly real time. And so I'd like to talk about three things that we use these seismic waves to study. One is to locate the earthquake. Two is to figure out what the size of the earthquake was. And finally, we can actually also infer a little bit about the fault plane that actually slipped to create the earthquake. But first, locating the earthquake. It's actually pretty simple, and it's not so different from the way you might use your intuition to figure out how far away a lightning bolt was, because you see the lightning and then you hear the thunder sometime later because the light travels much faster than the sound. And I showed you how P waves travel faster than S waves in the Earth. So if we can measure the difference in arrival time between the P waves and the S waves at 3 different stations, it gives us a sense for how far away that earthquake was. This is a schematic example here where there was an earthquake occurring at a plate boundary here, located, labeled as the epicenter, and then it traveled out and was recorded at 3 different stations. And on the right here is an example of measuring the difference between the P and the S wave time. And if we measure the difference between the P and the S wave arrival times, we can infer how far away that earthquake was. So for example, at seismograph A, we measured that there was a 3-minute difference between the P wave and the S wave. And that corresponds to the earthquake being about 1,500 kilometers away from the earthquake, away from the station. And then at seismograph B, we measured that there was an 8-minute delay between the P wave and the S wave. And this corresponds to the earthquake being about 5,600 kilometers away from the station. And then finally at seismogram C, there was an 11-minute delay. And the 11 minutes between the P and the S wave corresponds to a distance of about 8,600 kilometers. And so it turns out that there's only one place on Earth that's 1,500 kilometers from station A, and 5,600 kilometers from station B, and 8,600 kilometers from station C. And so we can triangulate then and figure out which place on Earth, what is the place on Earth for which this is true, and that gives us the location of the earthquake. Now in real life, of course, we almost always use more than just 3 stations, because the more stations we have, the more accurate our guess at the location is. But 3 is the minimum number that's necessary in order to be able to locate the earthquake. The second thing I want to talk about is how we measure the size of an earthquake. Now, at any location, here in Belmont or in California or Siberia, there are 3 factors that affect how strong the ground shaking is from an earthquake. The major one, of course, is the size of the earthquake. So the larger that earthquake, the stronger the ground shaking will be. But also, of course, the distance from the earthquake. If you're near the earthquake, you feel a lot of shaking, and if you're far from it, you do not. And then finally, more subtly, the properties of the rocks that the waves have traveled through. So some rocks make the waves lose a lot of energy, and other rocks don't. And so that'll also affect how strong that ground shaking is. And there are 2 main measures of the earthquake size. One is something called the Mercalli intensity. And intensity is measured by where you are. So it's not just one number for every earthquake, but if you're near the earthquake, that intensity factor will be higher. And if you're far from the earthquake, that intensity factor will be smaller. It's based on the amount of damage that was accumulated as a result of the earthquake. The other factor is the magnitude. And this is probably the one most of us are more familiar with. Whenever an earthquake's in the news, it's often reported along with a magnitude. And this is just one number for each earthquake. So we measure this from seismic records, not from damage, and it's useful for assessing how much energy has been released as a result of the earthquake. Richter magnitude is a common way to measure magnitude. However, it's not the only one, but it was one of the first ways to do it. And it's a pretty simple method. All it does is it says, well, if we know the S and the P arrival times, then as you saw before, that means we know how far away the earthquake is from where we're standing. So we measure that S minus P time, and that allows us to correct for distance. It allows us to correct for the fact that we're not very near the earthquake, but we're trying to estimate the size of the earthquake. So you measure that S minus P time on the seismograph. That's what's shown here. So in this example here, the P wave comes in at about 0 seconds, and the S wave comes in about 26 seconds later. And then we go down to this chart down here, and we put a little dot at the S minus P time of 26 seconds. So we put a dot there, and it turns out that that corresponds to a distance between us and the earthquake of about 220 kilometers. We then measure the amplitude of the largest wiggle in the seismograph, and in this case, that ends up being 23 millimeters. And so we go over to this axis here, and we put a little dot at 23 millimeters. And then we draw a straight line in between the S minus P time of 26 and the amplitude amount, and then where that line goes through this axis in the middle, that gives us the magnitude. So for this particular example, it was a magnitude of 5. And pretty simply put, that's how we estimate the magnitude of earthquakes, by correcting for the fact that if we're measuring the earthquake far from where it happened, then maybe the amplitude will be somewhat reduced, and then trying to back out what its actual size was. Now, interestingly, earthquake magnitudes follow something of a regular distribution. And I should say here that an important point is that a measurement of magnitude corresponds to a 10 times increase in ground shaking. And what I mean by that is that a magnitude 5 earthquake has 10 times more ground shaking than a magnitude 4 earthquake. And a magnitude 4 earthquake has 10 times more ground shaking than a magnitude 3 earthquake. So even though there's only an increase by 1 for each of those magnitude units, it actually corresponds to ground shaking changing by a factor of 10. So it's a pretty significant difference between, say, a magnitude 4 and a magnitude 6, because it's actually a 100 times difference in ground shaking. And as I started to say, earthquakes follow a pretty regular distribution, which is fairly interesting. And so, for example, we can say that every 3 years, these are the number of earthquakes that occur, on average, not perfectly, but pretty close. That globally, every 3 years, we have about 1 earthquake larger than a magnitude 8. We have about 30 earthquakes larger than a magnitude 7, 300 earthquakes larger than a magnitude 6, 3,000 earthquakes larger than a magnitude 5, and so on. So you can see that for each step down in magnitude here, we've increased the number of earthquakes by a factor of 10. And this is called the Gutenberg-Richter relationship, so that the number of earthquakes per year varies as a function of magnitude. And it actually doesn't really depend which region you're in or which time period you looked at. There's always this factor of 10 relationship between earthquakes of different magnitudes. And I'll give you an example here. In California, since 1816, there have been 180 earthquakes with a magnitude larger than 6. And there have been 24 earthquakes with a magnitude larger than 7. So there have been about a factor of 10 more earthquakes with a magnitude 6 than there have been with an earthquake of magnitude 7. And of course, there's been just 1 earthquake with a magnitude larger than 8. So again, even California, looking at this 200-year time period, follows this factor of 10 relationship, this Gutenberg-Richter relationship. On the other hand, in the central US, a totally different part of the country, not at a plate boundary, the numbers are different, they're smaller, but there's still a factor of 10 relationship. We have about 170 earthquakes with a magnitude larger than 4, 16 earthquakes with a magnitude larger than 5, and about 2 with a magnitude larger than 6. So again, every time this factor of 10 change. And it's pretty predictable, and this graph here just illustrates that relationship between magnitude and the number of earthquakes per year. So those are 2 things. We've talked about locating the earthquake and inferring the magnitude of the earthquake. And then final piece of information that I wanted to talk to you about is the fact that we actually have some information about the fault that slipped during the earthquake rupture. So if we look at this circle here and ignore for a minute the different colored quadrants, you can see that it's supposed to be a transform fault or a transform plate boundary, with the left side of the fault moving to the upwards direction and the right side of the fault moving in the downwards direction. So it turns out that the sides of the fault, that the areas of the rock that are being sort of pushed as a result of this plate movement we have colored them in here push. So on the left side, the movement is upwards, and so that quadrant gets labeled push. And on the right side, things are moving downwards, so the lower quadrant gets labeled push. And then the other two quadrants, the rocks are being pulled. And so the seismic waves then that are generated in these different regions have a different shape. And in particular, the P wave, that first wave to take off, is positive first and then negative if it's in a push quadrant. And it's negative first and then positive if it's in a pull quadrant. So you have compression going on in these push quadrants and dilatation or stretching going on in those pull quadrants. And so there's a relationship in the shape of those first P waves that tells us something about the earthquake, the way the fault slipped. And these are called focal mechanisms, or for obvious reasons, sometimes we call them beach balls because they sort of look like beach balls. And on the right here, I've put the three characteristic types of beach balls. So the simplest case, the one I just showed you, is on top. This is the transform fault, and this is the type of beach ball we see for a transform fault. In the middle, this is the type of beach ball that we see at a divergent plate boundary, so a place where we have stretching and extension going on. So it's colored in. You have pushing going on the outer rim of the beach ball, and then pulling in the middle. And at a convergent plate boundary, it's the opposite case, with pushing in the middle of the beach ball and pulling on the outer rim. Okay, so now that we've gone through this earthquake tutorial, I'd like to go back and talk for a little bit about these Chile and Haiti earthquakes. So first, back to Chile. Again, this was the earthquake that occurred on February 27th, 2010. It was a magnitude 8.8, one of the largest earthquakes ever recorded. And the map here is a zoom in on the region where the earthquake occurred. So here's South America over here on the left, and we've zoomed in on Chile, essentially, on the southwestern part of South America. Now there are a lot of different colored dots here. The big yellow star here is the epicenter of the February 27th earthquake. And then all those little dots around the yellow star are the aftershocks of that February earthquake. So you can see you have aftershocks, many aftershocks for starters, and they extend both south and north of the epicenter. The dots with the other colors, red, green, and blue, are historical seismicity in the area. So these are earthquakes that have occurred here since 1900. And you can see Chile is no stranger to earthquakes, and in fact Chile is no stranger to large earthquakes. Since the 1970s, 1973 I want to say, there have been 13 events in Chile with a magnitude larger than 7. So it's used to getting hit by big earthquakes, and in fact the largest earthquake that is known to have occurred in Chile in 1960. And that's shown down here. This little white dot is the epicenter of that big 1960 earthquake, and the white hatched area that I'm trying to outline here is the fault, the amount of the fault that ruptured during that 1960 Chile earthquake. So you can see that our February earthquake started just north of the 1960 earthquake, and then it extended up here as well. And you can see there are some labels, I don't know how well it shows up on the monitor, of previous historical earthquakes in the area, like 1906 and so on. So these are other large magnitude 7 and magnitude 8 earthquakes. Now here's the focal mechanism, or the beach ball, that was determined for this earthquake. It's plotted over here on Chile, and it's a little hard to see here, but you can probably see that it has some white on the left side, some yellow or gray in the middle, and then a little bit of white on the right side. So this is consistent with the type of beach ball I showed you before that we see at convergent plate boundaries. And indeed, this is a convergent plate boundary. You know now that this is where the Nazca plate is subducting or descending beneath the South American plate. So we have convergence and compression going on there. And the earthquake reflects the fact that that was the type of fault that slipped. Now this is going to be a little bit of a movie that'll show you how the fault rupture progressed during the earthquake. So on the left here is the area of interest. This is the western part of South America. You can see the cities labeled, Santiago and Concepcion. Here's the Pacific Ocean over here. Here's the continent. And there are little red dots that correspond to the aftershocks. And then the big red star is the epicenter of the February event. And on the right next to it is the same exact area. It just doesn't have these nice labels. But you can, however, see the aftershocks. They're outlined in white. And so when I press the movie to play, it's going to start showing up colors. And this is going to be how that rupture progressed. So it's a large fault area, and the rupture started here at the epicenter, and then it's going to move first a little bit south, and then it's going to move north, and there'll be a little counter up here in seconds that will tell you how long the rupture took. So let's give this a try. Okay, so you can see it started. All right, there's all that white. That's the amount of fault that's slipping within the first 30, 40, 50 seconds, and then that white part is moving to the north as the fault continues to slip, and now we're 120 seconds or so, and there was still some fault. So this fault slipped for at least 2 minutes, slightly more, to produce this magnitude 8.8 earthquake. And I'll show you that one more time because it does go by pretty fast. So look for those bright white colors that start to light up. That'll show you where the slip on the fault is happening. So it's not all just happening at one place, and it doesn't happen instantaneously, but instead it takes place over a couple minute period of time, and it covers several hundred kilometers in length of the coastline. So it's not just going to be one particular area that's affected by this earthquake, but it actually covers quite a large region. And this figure here is a current theory for why the rupture stopped where it did. So it didn't just go on forever, it didn't just continue up the whole coastline, but it did stop. And this is showing, it's a bit of a weird perspective, but we're in the Pacific Ocean down here, and we're looking we're looking eastward towards South America. So north is up to the left, and south is down to the right, and this is the Pacific, or the Nazca Plate that's coming in and subducting beneath South America. And the colors here show the bathymetry of the seafloor. So it's actually about 1 kilometer deeper to the north and 1 kilometer shallower to the south. There's a step in the topography of the seafloor here, and this is a fracture zone. And it turns out that where that rupture stopped, and also essentially where the aftershock zone has stopped, where we don't see aftershocks occurring anymore, is about where this step in the seafloor is. So it's possible that there's something a little bit funny about the seafloor that's being subducted here, and it may have helped to abbreviate or halt the propagation of that rupture because there's some sort of asperity in the oceanic plate that's being subducted. And I've mentioned how this 8.8 earthquake is one of the largest events we have on record, either historical or instrumental record. And this figure here shows the global earthquakes that have occurred with a magnitude larger than or equal to 8. So since 1900 to today, 110 years, how many earthquakes have occurred that have a magnitude larger than 8? It's only a handful of earthquakes. And so the bottom figure here is showing the magnitude going from 8, 9, 10, and it starts at 1900 all the way to the present. So you can see the 5 largest earthquakes that we've recorded in the last 110 years. The largest one is that Chile 1960 earthquake, magnitude 9.5. The second largest one was the Alaska earthquake, the Good Friday earthquake that occurred in 1964. And then the Kamchatka 1952 earthquake is pretty well tied with the 2004 Sumatra earthquake in terms of size. And then this most recent Chile event is the 5th largest. So only a handful, and it's pretty significant to have such a large event occur. And the stars in the map above show the locations of these large earthquakes, and you can see that they almost all, with a couple of exceptions, occur along convergent plate boundaries and especially at subduction zones. I mentioned that the Chile earthquake generated a tsunami, and there was a lot of concern about the damage that tsunami could do as it propagated through the Pacific Ocean. And the way a tsunami works is that you need to have some sort of displacement at the seafloor. And what happens with a thrust fault, like we had to produce the Chile earthquake, is it causes one side of the seafloor to move up relative to another. So the thrust fault makes the seafloor move up just a little bit, it displaces some of that water, and it creates a pulse of water at the top of the water column at the surface that then has to spread out and move like a wave. And tsunami waves, if you were in the deep ocean, you'd barely notice them. But they slow down in their speed once they reach the coast. And so since you have the front part of the wave slowing down as it reaches the coast, but the back part of the wave still traveling very fast, then the back part catches up with the front part, and you end up with a very tall wave height. And that's sort of the basics for how tsunamis work, and how the tsunami that was generated in Chile worked as well. And here is just a preliminary forecast for the tsunami height that was predicted to result from this Chile earthquake. So there was concern about it having an effect pretty much all throughout the Pacific Ocean with heights of several tens of centimeters or hundreds of centimeters. And then just a couple slides about the Haiti earthquake. And I think it's actually interesting to compare the Haiti earthquake with the Chile earthquake because they occurred so close together. They were both very damaging and devastating, and yet in many ways they were different. These two maps here are now comparing the location of the Chile and the Haiti earthquakes. So the location of the Chile earthquake is shown on the left. Again, it's that coastline along western South America, and the star shows the epicenter. And this box surrounding the Chile earthquake, that's the area of the fault that ruptured. So that movie that I showed you before, this box then encloses that entire area that ruptured. On the right is the Haiti earthquake, so we're zooming in on the country of Haiti, and you can see the star right there. That's the epicenter of the Haiti earthquake, and that little box around it is the fault that slipped. Now these two maps, if we can zoom out and look at them together, are actually drawn to scale. So the box surrounding Haiti and the box surrounding the Haiti earthquake and the box surrounding the Chile earthquake are meant to be compared. In other words, the Chile earthquake, the fault that ruptured in the Chile earthquake, was 200 times larger in size than the fault that ruptured in the Haiti earthquake. The difference between this little rectangle here, and the big rectangle here is meaningful in terms of size. So a magnitude 7 is much, much smaller than a magnitude 8.8 earthquake. So why was the Haiti earthquake so much more damaging? A couple of reasons. One is the fact that it was actually occurred shallower in the crust than Chile. So Chile occurred at about 35 kilometers depth, so several tens of miles, whereas the Haiti earthquake was at about 10 kilometers. So if it's closer to the surface, it's going to cause more shaking at the surface. Second is the fact that the Haiti earthquake occurred in such a populated part of that country, and of course the difference in the construction standards between Chile and Haiti had a factor, has to be taken into consideration again. And then I'll conclude by showing you the focal mechanism for the Haiti earthquake. So it's again another beach ball, and perhaps you recognize it now as a beach ball that occurs along a transform boundary. So it has that sort of classic 4-quadrant look. And in fact, indeed, that is the fault that we think that the Haiti earthquake occurred on. It occurred on a transform fault in this region, and it's a little hard to see here, but if it's possible to zoom in on the region of surrounding Haiti, and you can see there are a bunch of lines that go through the country. And in particular, there's one line that goes through the southern part of the country and one line that goes through the northern part of the country. Those are both transform faults. They're part of the fairly complicated plate boundary in this region. And it's this southern fault here. It's labeled EPGF, which stands for Enriquillo Plantain Garden Fault. It's along that fault that we believed the Haiti earthquake occurred, and it was again a transform plate boundary. So I'll stop there, and I'll be happy to take any questions from the audience.